Hello, John Crooks here with the second in a series of presentations on pitch and pitch systems in music. In this presentation, we will use an oscilloscope, which is a mechanism we can use for visualizing waveforms, to define and examine what the octave is in terms of the audible frequency spectrum, and how the octave can be used to define a pitch system such as the ones we use in music. So without further ado, I will turn it over to our first presentation using the oscilloscope. So here's our oscilloscope. In this case, it's actually a bank of 4 oscilloscopes. Each yellow horizontal line is going to be used to display one kind of waveform. And here's our first waveform that we're going to look at. We see it scrolling across the top of the screen. Here's a pitch and its waveform. The pitch is 220 Hertz, which in our system we call A3. And there we can hear it. When we play a pitch with twice the frequency, or 440 Hertz, which is called A4, we form a 2-to-1 ratio with the first pitch. And so here we see that ratio in action. And here we hear the two pitches. There's that low 220, do, and the upper 440, do. This is the octave. Notice how the 440 Hertz waveform cycles exactly twice as quickly as the 220 wave. So here's one cycle of our 220 Hertz wave, and then we get for that 2 cycles of the 440 Hertz wave. Octaves form the basis of the pitch system used in Western music, and this is very important and pretty cool. For most people, pitches in a 2-to-1 ratio sound similar, and I know that's true for me. I hear this lower A, do, even though it's different than the higher A, do, in terms of a frequency in Hertz, they sound somehow the same to me. They both have a sound that is equal in my ear. This phenomenon is called octave equivalence. In the Western pitch system, pitches in 2-to-1 ratios have the same letter name. So here we're looking at 2 pitches called A. In our Western system, all pitches with the same name, such as C or D or F sharp, have this 2-to-1 octave relationship. This is one of the ways our ears cope with the very wide range of audible sound. When 2 sounds form a 2-to-1 ratio, we can process them using similar neural pathways. So we hear through this very wide ratio of 1,000 to 1 in audible frequencies, but when we hear 2 things that form this 2-to-1 ratio, we kind of have the same way of processing them in our ears and in our brain. It's interesting that our ears categorize pitches using the same 2-to-1 ratio found in the range of our visible spectrum. With light, we see a rainbow of colors within a 2-to-1 band of frequencies. With pitch, we have this huge 1,000 to 1 range of audible frequencies that we can organize using octaves. Each octave is a kind of mini spectrum. In Western music, the ratio between 2 pitches is called an interval. The 2-to-1 octave is the most basic example. And I just want to point out something about this octave, which is that our ears are so sensitive that we can hear very small changes in this. So if I just change it by a couple of hertz, we see in the waveforms that it's not quite as in tune as it was before, but also we can hear with our ears that this is no longer an in-tune octave. Our ears are very sensitive. Now let's look at another musical ratio. Taking our 440 Hertz A, let's add a 660 Hertz wave. This is called E5 in our pitch system. 660 to 440 is a 3-to-2 ratio. This ratio is a perfect fifth, which is very common in music and a key component of the Western tonal system. Notice how the lower pitched wave cycles exactly twice for every 3 cycles of the higher pitch. So let's look at that first. Here's 1, 2 cycles of the lower pitch goes for 1, 2, 3 of the higher pitch. Now let's hear this perfect fifth. It's going to be a very familiar sound. Do, do. So this perfect fifth is a very important part of how we organize our pitches. We take the 2 to 1 interval, which is almost universally heard as a similar kind of a pitch, and we add to it this 3 to 2 relationship. Now, if we add this 660 hertz wave and the 880 hertz, which is an octave above our initial 440 hertz A, we get a 4 to 3 ratio, and this is a perfect fourth. Do, do. Here's the lower component, and here's the upper component. Do, do, do. So now we have 3 different intervals just using some basic ratios. We have a 2 to 1 octave, a 2 to 3 fifth, and a 4 to 3 fourth. So this 2 to 1 ratio is a very common, in fact almost universal way people organize musical pitch. The 2 to 3 and 3 to 4 ratios are very important in the Western tonal system and reveal that musical intervals in our tonal system are ratios. Every musical interval uses a very specific ratio. No matter what frequency range, whether it's high or low, we use, intervals will sound more or less the same because of the ratio of frequencies is what we use to organize tonal hearing. So let's look at all of these things together now. We hear our low pitch, do, then we hear do, the octave, and a fifth, da, and our upper octave, da. And within this we have 3 different kinds of relationships. An octave that goes from do, do, a fifth that goes do, do, and a fourth which sounds do, do. And it really is the octave that allows this kind of subdivision of the spectrum that we can hear, which is 1,000 to 1, a little bit too wide for us to parse easily, into little 2 to 1 ratio chunks. And then further, our ears are able to hear certain kinds of relationships like 2 to 3 or 3 to 4, and further refine our sense of how the pitch system works in Western music. So there, we've done it. We've used an oscilloscope to visualize simplified waveforms that show us how certain pitch ratios, such as 2 to 1 or 3 to 2 or 4 to 3, can be heard by our ear, and especially the 2 to 1 octave helps us to further subdivide and parse the very wide range of frequencies that we can hear. So just as we see through about a 2 to 1 ratio of frequencies in light, when we hear a 2 to 1 ratio in audible frequencies, we hear those pitches as kind of the same, and within that we have a little mini chromatic spectrum of hearing. Now, these relationships of 2 to 1 and 3 to 2 and 4 to 3 are not just basic parts of our tonal system, they are also basic parts of how musical instruments function. And these intervals are sometimes called just or pure intervals. Let's take a couple of moments and look at how these just or pure intervals can be found in the vibration of a string, and then take another few minutes to look at them using an oscilloscope in a different way. So here's our next part of pitch and pitch systems: overtones, just intervals, and the building blocks of tonality. We've learned that our brain uses ratios to parse a wide audible frequency range. In the Western tonal system, the phenomenon of octave equivalence is used to create a kind of spectrum of 2 to 1 ratios within the large range of audible frequencies. And so here we see a piano keyboard, and just as a metaphorical example, we see a spectrum for every octave. So in this example, every D has a certain color, every D sharp has a certain color, and that is indeed a little bit how our ear parses the wide range of audible frequencies we hear in music. Even without perfect pitch, we use our sense of relative pitch to hear how these interval ratios are being used in tonal structures. Simple ratios yield basic musical intervals. 2 to 1 is the octave, 3 to 2 is the perfect fifth, and 4 to 3 is the perfect fourth. When we look at waveforms, as we just did, we can see how these waves are related to frequencies. These relationships are also a basic part of how our musical instruments work. Here we see a diagram that is a sort of schematic of a vibrating string. When a string or a column of air vibrates, we hear the fundamental pitch, which could be also seen as the top example of these four, as well as many partials or overtones, the remaining three. This picture shows the fundamental frequency and the first three partials. The partials form whole number ratios with the fundamental pitch. When we isolate the partials, we hear harmonics that reflect the intervals we just found. A 2-to-1 octave, that's the second from top, a 3-to-2 fifth, and a 4-to-3 fourth. Partials extend to very large ratios, including 7-to-1, 13-to-1, etc., and are an important aspect of timbre, timbre being the variety of partials that contribute together to form the overall color of a pitch. The whole set of overtones is called the harmonic series. Here we see a high-speed camera capturing the high partials of a bass string, and we can see here this camera, which has a shutter speed that's going very quickly, is capturing some of the waveforms of the string while it is in motion. So whenever we are hearing a pitch coming from a musical instrument, that pitch is made up of the fundamental pitch, which is the lowest one that we can hear, and then a series of overtones or partials. And it looks here as though the camera is capturing perhaps even the 10th or 11th partial of this string vibration. The whole number ratios we find in the basic intervals and the harmonic series are called just intervals. We've looked at 2-to-1, 3-to-2, and 4-to-3 intervals. These intervals and a few more have special qualities. Their sound can be described as pure. Now let's look at them using a different kind of oscilloscope. So now we know that pitch systems use this phenomenon called octave equivalence to subdivide the audible frequency range, which is very wide, into smaller chunks that represent 2-to-1 ratios of frequencies. And we've even seen how these waves look in simplified form, and that cool video of the bass string vibrating underlines how these waves can be found as component parts or partials of the music we hear every day coming from acoustic instruments. Let's take a different kind of oscilloscope that adds waves together and look at that to discover more about just intervals, which form simple whole number relationships like 2-to-1 for the octave, 2-to-3 for the perfect fifth, etc. This oscilloscope adds waves together. Here's a 220 Hz wave like the one we were looking at in our first example. And here we can hear the pitch again. Do. When we add a 440 Hz octave, we see the two waves interaction. It's very smooth and regular. We can hear the same two pitches, but we see a different kind of a waveform. This very tall peak is the lower pitch, and the smaller one is the two pitches interacting. Again, we can hear that octave, do, do, two A's. We hear them as the same because of octave equivalence. Now, the same smooth waves can be seen in these summed 3-to-2 fifths. Do, do. There's our lower pitch, do, and the higher pitch, do. And for our 4-to-3 fourths. Do, do. We notice that in each case, the waveforms are very smooth and regular and show some pretty cool patterns. When we add all four waves, the waveform is still very regular. This is a simple example of just or pure frequency relationships. All of these simple whole number ratios, when we add them together as waveforms, show how these sounds are very stable. Now, notice how even a tiny change in frequency, here I'll change the 880 Hz wave, it radically changes the wave appearance. We can hear the intervals leaving a just relationship. And again, it only takes a few hertz for us to really be able to hear these differences. Let's try it with the octave. I'll change the lower pitch, the 220 hertz pitch, and we'll see the wave change from a smooth, just relationship to a more complicated relationship very quickly. And within just 17 hertz, we have something that really does not sound like an octave at all anymore. So these just intervals include the octave, perfect fifth, perfect fourth, and major third. Their sound is described by some as stable, strong, or at repose. The simple ratios and pure sound form the basis of the Western tonal system. Surprisingly, although we see these pure ratios as being a very important part of, first of all, how we parse the large audible spectrum into smaller units such as the octave, and also we hear them in our music all the time, the octave, the 2 to 3 fifth, etc. We don't find these pure ratios in equal temperament, which is the standard tuning system for pianos and many other instruments. So let's take another moment and look at our summed pitches. Here is one pitch and then the octave, the 2 to 3 fifth, the 4 to 3 fourth, and then all summed together. We hear do, do, da, do, and we only have to change a pitch by a small amount to cause a lot of disturbance in the waveform. So that brings us to the end of our second episode in our continuing series on pitch and pitch systems in music. We've covered a lot of ground in this presentation, starting with a look at how frequencies can be shown using an oscilloscope and how certain relationships between frequencies, such as a 2 to 1 ratio and 3 to 2, become the building blocks of our tonal system. With octave equivalence, we have a phenomenon that is very interesting. It allows us to create smaller spectrums within the large audible spectrum that are comprised of a 2 to 1 relationship. We hear this all the time in our tonal music, such that every C to every C an octave apart is a 2 to 1 ratio. This is a very helpful way for us to begin organizing pitch systems, and indeed these simple whole number relationships are found not just in our musical pitch systems, but in the vibrations that our instruments make. We saw a bass string being captured at its upper partials, and then we saw how when we add waves together, we can see how just intervals have very stable and smooth waveforms, and all we have to do is change a frequency by a little bit to throw all of this stuff off kilter. Our ears, since we're accustomed to listening to Western tonal music, similarly can hear when an octave or a fifth or a fourth is in tune, and we tend to have a very strong reaction and understand when pitches are not in tune. So coming up in future episodes, we will look at the major third, then the triad, and later on we will get into the system that is used for pianos today, which is called equal temperament. One very surprising aspect of our equal temperament system is that other than the octave, there are no simple whole number ratios in the system. There are no 3 to 2 perfect fifths, and other intervals are also not pure. So we will discover why that is in future episodes.